Hello, we are the NTNU robotics team, and this is our contribution to the 2020-2021 robotics competition. My name is Magnus Steinstad. I'm an industrial cybernetics student, and I previously have a degree in computer science. My main responsibility is the control system, and I'm also the student team leader.
My name is Benedicte Gjersdal. I am a drilling engineering student, and my main responsibility is the mechanical and hydraulic design.
My name is Gaute Honsenar. I'm a drilling engineering student, and my main responsibilities in this project are BHA design and finance.
My name is Trygve Mikael Vigga Skretting. I'm a drilling engineering student, and my main responsibilities are HSC and bit design.
The rig operates 3 motors. One motor is used to hoist the drilling component up and down on a ball screw, applying weight on bit. The next motor enables azimuth change. The last motor provides bit rotation by means of a long, thin rod. The rod is connected in the top drive motor and in the BHA. It rotates inside the azimuth system, hydraulic swivel, and inside the drill pipe. The most challenging aspect was the rod twisting off while drilling. The solution was to change the top drive motor, increasing maximum RPM from 380 to 1300. The rod was also changed from aluminum to titanium. The lessons learned from this was that low RPM with high weight on bit generated torsion, which twisted the rod. The pictures show the torque spikes when the rod twisted. The team also learned that through trial and error, aluminum rod proved too weak. Steel, which allowed for less bending, was better, but still twisted. Finally, the team chose titanium, which was the best fit with respect to shear strength. Titanium was early investigated last year, but left because of its high cost. In retrospect, the team should have invested in the costly titanium rod. However, this forced the team to educate themselves about different material strengths and the forces present during drilling operations, such as rotational and axial forces.
The BHA is designed to build an appropriate angle with respect to the 30-degree inclination requirement. It is also designed to house and protect the download sensor card properly, while simultaneously allowing for torque and rotation transmission from top drive motor to bit. As shown in the picture, the BHA is made up of 2 stabilizers: a sensor housing, a bend sub, a universal joint, a drive shaft, a packer, and a bit sub. The stabilizers stabilize the BHA in the borehole to reduce vibrations and offsets. The sensor housing is a thick-walled cylinder with a compartment that houses the sensor card, sealed off with liquid rubber and epoxy glue. The rod is connected to a universal joint by a sleeve that is compressed by 2 set screws. The universal joint is welded on the drive shaft that runs through the lower stabilizer and into the bit sub. The packer located inside the near bit stabilizer is made of PEEK, allowing for concentric rotation of the bit sub and bit regardless of the packer and near bit stabilizer. It also has 2 toroidal seals to guide the water through the drive shaft. Several changes have been made to the BHA after phase 1. The drive shaft have been increased in diameter to increase the strength. The universal joint was welded onto the drive shaft to further increase the strength in the connection point. To allow for the sleeve to get a better grip on the rod was filed down to achieve 2 flat sides. The bend sub angle has been increased to build more angle. All these measures were done according to results from drilling tests to improve the design and prevent future fails and challenges. In case the sensor card fails, a backup solution is implemented and ready for use for easier sealing and protection, as shown in the picture. The team have learned that the performance of small components in the BHA can have a major impact on the system in total. An important lesson learned is that changes in one part of the system may lead to challenges in another.
The team has 15 different bits available, where we have made 2 different bit designs, and Lyng Drilling, which is a Schlumberger company, have produced the 2 bits for us. The process ending up with their own bits started with a visit last autumn to their production plant, which is located across the fjord of Trondheim. The picture to the right is showing the team at the production plant. When studying recent years' reports from NTNU and other universities, it was observed that the provided bit by DSATs experienced many problems with respect to instability leading to vibrations. The desats bit did not function well with a design involving a bend sub. The problems were also experienced for us when testing the desats bit. The vibrations led to many errors, for example broken set screws and broken drive shaft. It experienced problems with stability which led to extensive vibrations. This instability could be explained by the flat bit profile for the desats bit. A flat profile is not beneficial with respect to stability. For a rotary steerable system, a flat profile could be suitable, but with a bend sub, stability is more important. Because of this, has the self-designed bits a short parabolic profile with deeper cone angles than the desats bit. We did also purchase different bits from Alibaba that has performed well. The bits provided by Lyng Drilling were further improving the drilling performance. In addition to deeper cone angles, the bits have more cutters that leads to less rock volume to cut per cutter and a longer gauge length that helps with stabilizing. The average ROP measured in centimeters per minute was improved from 0.5 to 1.5 centimeters per minute to between 3 to 7 centimeters per minute depending on the weight on bit. The bits did also minimize torque spikes and vibrations by a lot compared to the Alibaba and desats bit. This is very positive for the rod and connections in the BHA.
We have a sophisticated control system developed in MATLAB and Simulink. The control system has been completely redesigned to allow simulations and fast-paced prototyping of advanced position controllers to meet this year's competition objectives. The downhole sensor is a modified Arduino microcontroller used to estimate the orientation of the BHA. Modeled and unmodeled Kalman filters estimate orientation from accelerometer and magnetometer data. It was discovered that vibration patterns while drilling made real-time estimation of orientation difficult. Automatic orientation surveys are therefore executed at regular intervals. Between each survey, the position estimate relies on model predictions. The positional model assumes that the BHA will move in the direction of its current orientation at the movement velocity of the hoisting system. Orientation is expected to change at a certain rate in the direction of the BHA bend. The azimuth control steers by orientating the BHA bend while drilling to follow a Bézier well path reference. A nonlinear model predictive controller, or NMPC for short, is used. NMPC will run optimization simulations with different azimuth velocity inputs to predict and find the best inputs based on a cost function before applying the first optimized input to the system. A future well path prediction is shown in real time and displayed in a 3D plot together with the current position, current well path, the Bézier well path plan, and the target points. The rig can be manually controlled by an operator from a user-friendly human-machine interface or using an OPC UA API. Relevant data is displayed to the operator in real time. The autonomous system is based on a state machine. Current operating mode is displayed to the operator in the human-machine interface. High computational cost requires the control system to be run as a distributed system on 2 different computers. Incident detection and additional safety features are implemented. Most notably, a stuck bit incident detection system will automatically lower weight on bit if the bit gets stuck within a few tenths of a second. Stuck bit is detected from a spike in top drive torque.
To verify if the received sensor data were accurate, runs where we drilled out of the rock were done. We drilled both through the bottom and out through the sidewalls. Afterwards, we used a ruler and a protractor to verify position data, like for example inclination and azimuth. The results were very positive and confirmed that the sensor card was satisfactorily accurate enough.
The NTNU Drillbotics team is granted a sponsorship of 25,000 Norwegian kroners from Equinor. The rest of the budget is covered by BRU21, which is NTNU's research and innovation program in digital automation solutions for the oil and gas industry. This year, due to COVID, the team was advised by the NTNU administration to stay within a limited budget of 75,000 Norwegian kroners. By looking at the budget presented here, we managed to stay well within the budget, as our total expenses ended up at approximately 64,000 Norwegian kroners, equal to approximately $7,600 US. Important lessons learned with respect to the budget is that it is important to leave room for a buffer in case of unforeseen incidents and expenses. Good planning results in great results even when your budget is tight.
This is our contribution to the 2020-2021 robotics competition. The competition objectives have challenged us to collaborate across disciplines and find innovative solutions to industry problems. We are confident that the project has prepared us for our future careers, and we are proud of what we have accomplished.